Good morning, everybody. Welcome to the High Energy Density Science Center Seminar Series. I am pleased to have with us today Dr. Snejana Arbaji, who is Professor and Chair of Applied Mathematics at the University of Western Australia. Before she worked at Carnegie Mellon University, the University of Chicago, and Stanford University in SUNY Stony Brook in the USA, and also at the Osaka University in Japan and the University of Bayreuth in Germany. She got her PhD at the Landau Institute for Theoretical Physics of the Russian Academy of Sciences. She is a theoretical physicist and applied mathematician specializing in dynamics of fluids and plasmas and their applications in nature and technology. Her key results are the mechanism of interface stabilization, the special self-similar class in the interfacial mixing, and the fundamentals of Rayleigh-Taylor instabilities. Her key contributions to the community are the program Turbulent, Mixing and Beyond, and the editorial work. Her advancements are recognized nationally and internationally by the National Science Foundation and National Academy of Sciences in the United States, Japan's Society for Promotion of Science in Japan, and the Alexander von Humboldt Foundation in Germany. She was elected Fellow of the American Physical Society for deep and abiding work on the Rayleigh-Taylor and related instabilities and for sustained leadership in that community. And she serves on the APS Committee on Scientific Publications. So today's talk is being recorded, so please be aware of that. And also it's an unclassified talk, and be aware of any export control issues. If you have any questions and you're online, please enter them in the chat field and I will read them at the end. And if you're here in person, let me pass the mic to you so people online can hear you. Thank you, and please enjoy.
Thank you so much. I would like to express my gratitude to Lawrence Livermore National Lab and Physical Sciences Division, and particularly to Fran Graziani, Paul Grabowski, and Bruce Remington, who invited me here, as well as to Jessica Carlton, who actually made a lot of technical work, and to the colleagues who are now working on the recording. I will be presenting today the interface dynamics, the problem on interface dynamics and flow field structure in ideal and realistic fluids. These problems are associated with instabilities in plasmas instabilities such as ablative Rayleigh-Taylor and Richtmeier-Meshkov instabilities. However, no electromagnetic effects will be considered. Essentially, we are talking about neutral plasmas. The work is theoretical, mathematical. So please, just where you will see a lot of formulas, just breathe in, breathe out, I will walk you through. So it will be, I hope, an enjoyable, enjoyable journey. I would like to thank my colleagues with whom this part of the work was conducted. These are some of the papers which have been published. And Leo Kadanov and Sergei Anisimov, they passed away. But Leo Kadanov, he actually did have we had a lot of discussions with him about this paper. And I believe that, there are University of Western Australia and National Science Foundation, they supported these developments. So I skip the slide on who I am, because thank you so much, Paul, for the nice introduction. But before I will be starting, since it is an extended sort of tutorial, even though I'm not in a position to teach people here, because it's a highly distinguished, highly professional community, but still, I would like just to mention that on the problems that we work on, they are also actually somewhere at the border between mathematics, science, and engineering. And whenever we solve these problems, we need to keep in mind that mathematics, science, and engineering, they might approach the same phenomenon or the same sort of problems, type of problems from the different perspectives. Specifically, mathematics studies things that don't exist in nature, such as number, functions, derivative, integrals, functionals. They don't exist in nature. They exist only in our mind. And we need to get a precise knowledge about the project that exists only in our mind. Whereas science, on the contrary, does not care about our mind. It does not care what we think about a particular process, but it does study things that do exist in nature. Whereas in engineering, we control things that are man-made, and we try to get information with account for as many minds and as many processes without, getting into details. What is the behind this process? What is the actual cost for the process to occur in order for the things to work? Even though they sound very different, they do have one thing in common, and I believe that actually what we need to have in common, there should be an opinion-independent result. Not only a result that depends on the consensus in the community, but also actually an opinion-independent result that actually makes a community or unites a community. So I will be discussing today the interfacial mixing from microscopic to macroscopic scales. And this is maybe one of the first massive molecular dynamic simulations. I think it was Bernie Alder from Lawrence Livermore National Lab and Kai Kado and other colleagues from Los Alamos National Lab. And you see the development actually of Rayleigh-Taylor instability, which is actually presented on these slides here, when an initially flat interface between heavy fluid marked in red and light fluid, heavy fluid marked in red and light fluid marked in blue is slightly perturbed. Then the perturbations start to grow, and then they grow, and we have actually an interfacial mixing that is developed over here. However, if you'll take a piece of material here, it's very sensitive. If we have a piece of material here at the interface, zoom it in, and zoom it in, we see that even in a small piece of material at the interface, we have a mixture, essentially molecular mixture of the processes. So if this would be essentially the diffusion process, the interfacial mixing is not the same, physically not the same as a molecular mixing process. The motivation for this problem is that for these problems to consider is that the interfaces and interfacial mixing, they exhibit non-equilibrium dynamics, and they couple microscopic to macroscopic scales, as I have just illustrated. And they govern a broad range of processes in fluids, plasmas, materials, at astrophysical scales, at atomic scales, in low energy density regimes, and high energy density regimes. Their understanding have a critical importance for science, mathematics, and engineering, as well as for energy and environment. We focus in this work on stability of a phase boundary that is broadly defined. And we develop the rigorous theoretical framework, capture the physics of non-equilibrium dynamics, and chart perspectives for the future research. So what interfaces are? Interfaces might appear obvious at the first glance. We kind of believe that interfaces is something like a line separate one material from another. However, they are challenged to rigorously defined. The common knowledge is that the interface is thick, maybe somewhat diffusive, and has some fluxes of, for instance, heat and mass, or maybe something else across it. Whereas the front is a sort of approximation of a very thin, non-diffusive interface that might have zero fluxes. However, especially in high energy density conditions, we might have interfaces that may be very thin, such as nanometers, few nanometers thin interfaces, and that might have macroscopically observable significant fluxes of mass and heat, and maybe some other species across it. Also, the common wisdom is that in this case, when we have an interface, it may be stable or unstable, but when it's stabilized, it is stabilized primarily by microscopic effects. I'm saying microscopic purposefully, even though it should be pronounced like microscopic, so not to confuse with a macroscopic. So it's a microscopic with an I, microscopic with an I. And microscopic mechanism is essentially a mechanism that involves interaction of many particles at microscopic scales, essentially at kinetic scales, which may be thermal conductivity, some dissipation processes, some surface tension. So everything that is which is a result of an interaction of many particles at kinetic scales. Our results actually show that these definitions, these common wisdom approaches, they might be obvious, but they actually contain, there is a need to reconsider them. And according to the theoretical analysis that we obtain, interface is the place where balances are achieved. And these balances are achieved by linking microscopic scales to microscopic scales to macroscopic scales. Interface is stabilized primarily by macroscopic inertial stabilization mechanism. It's a new mechanism that we are going to discuss. Interfaces can be destabilized by the acceleration. Interface structure of macroscopic fields in the bulk, this is actually the main result that we are obtaining, is set by the microscopic transport at the interface. So in other words, whenever we have a bulk actually adjusts to what we have at the interface, not the other way around. And what we also found that thermal heat flux and microscopic thermodynamics is responsible for creation of vertical fields in the bulk. Essentially, the vertical fields are essentially energetic rather than dynamic in nature. We discovered actually new fluid instabilities for ideal fluids, including conservative dynamics, and for realistic fluids in the three regimes of advection, diffusion, and low Mach number. And we also considered the classical Landau 94 prospect. It's actually a so-called third prospect of Landau, for Landau-Darrier instability. And we have shown that this solution, which was a point of a confusion for many researchers for many years, is just a perfect mathematical match. If I would like to summarize actually the outcome of the studies, is that we need, according to our theoretical mathematical analysis, interfaces, first of all, they are real. It's not like ghost structure. They are real, they exist. They are globally stable, and they are stabilized primarily by inertial stabilization mechanism, and they can be forced by acceleration to destabilize. Interface dynamics is important to study because, you know, these unstable interfaces and interfacial mixing controls processes at astrophysical scale, such as interstellar medium, core collapse supernova, thermonuclear flashes and so forth for compact stars, inertial confinement fusion, magnetic fusion, z-pinches, light material interaction, material transformation under impact, multi-phase geophysical flows in ocean and atmosphere, as well as energy and environment. For an interstellar media, like, you know, for instance, we see these big structures which are look like stalactites or stalagmites. They are light years long. These are clouds of molecular hydrogen. The fingers protrude from the wall of a vast cloud of molecular hydrogen. And the cloud stiffness can be caused either by the magnetic pressure or by some ablation pressure by ionizing radiation of nearby stars, as it has been discussed by researchers, like, you know, some time ago. So it's a sort of appearance of interfaces at astrophysical scales. Supernova and nuclear synthesis is actually the final process of existence of a star, essentially death of a star. And even here, we may already see, like, you know, that in general, even in nature, we might see, like, you know, two sort of type of interfaces. One of them, this would be interfaces, and this may be associated with the dynamic of type 1A supernova. In this case, the interfacial mixing that predominates propagation of thermonuclear flames front and provides condition for synthesis of iron peak elements. Whereas type 2 supernova is actually sort of usually Rayleigh-Taylor mixing. It's an interfacial mixing of layers of the progenitor star. It provides condition for synthesis of heavy mass elements. Now, for the fusion, I probably would not need to discuss a lot here, because essentially we might have situation when we have fronts, it would be a direct drive situation. And in the United States, these are usually an Nike laser or a Gecko laser when the laser beam irradiate directly the targets. Whereas we might have also indirect drive, and which is implemented in the National Ignition Facility. And we actually see this, you know, great successes that has been recently achieved. And I very much hope that it will be, everyone I think hopes that it will be continuous progress, and wishes the best success to the colleagues. Material melting and evaporation is another application of, actually another potential application of interfaces and mixing. In this case, we actually have, for instance, molecular dynamic simulations of material melting with the Leonard-George atoms, and we see, like, you know, how the piece of metal, when it was shocked, essentially start to melt, forming interfaces and like small droplets here. Or it may be the molecular dynamic simulations of, for instance, Richtmeier-Meshkov instability, or a smooth particle hydrodynamic simulations of Richtmeier-Meshkov instability that is presented here. One thing that we would like to mention where the interfaces are particularly important is the situation when we might have potentially chemically reactive flows. And this is actually reactive force field simulations. And what is interesting that when we start model chemically reactive flows at, for instance, at macroscopic scales, we usually come with the concept of a single reaction constant that dominate the process. However, in this case, these simulations, reactive force simulations, they illustrate that when the chemical process is as simple as the decomposition of hydrogen peroxide, one may observe the, like, you know, 5 different species and 7 different reactions, each coming with a particular specific reaction zone. So actually the chemically reactive processes, as we might now see from the, which form the interfaces actually here, they might be more complex than we traditionally think about them at macroscopic continuum scales. What is even it was also interesting finding of these simulations that in fact actually the energy distribution in these systems at molecular scales, it may be different from traditionally presumed, like, you know, energy diffusion, which also associated with like, you know, multiple collisions, inelastic collisions of fluid particles. And in this case, rather than actually colliding and diffuse the energy may be also scattered rather than diffusing. And in this case, I'm sorry, different, like, you know, not translational, but rotational and vibrational degrees of freedom of the molecules can be intensively used. Now I would like to actually illustrate with the examples from nature. It's a multi-phase geophysical flows, the fact that interfaces are stable at global scales. because they indeed tend to be stable at global scales, even when we have fluxes of mass and heat and maybe some other species. And these are two illustrations. One of them is when waters in two oceans meet and don't mix for a very, very long time. So we observe actually one ocean and another. An interface between them is well defined and stable, even though slightly perturbed. And the other example is when two rivers meet and do not mix. It's a confluence of river, of Green and Colorado rivers in Canyonland National Park, which actually is a phenomenon also known for a very, very long time. So our theory actually explains this phenomenon because one of our conclusions, as I mentioned earlier, that interface is globally stable unless it is forced to destabilize. Any question? Okay, good. Now, of course, there are many other examples, particularly like, in addition to problems of scientific interest or technology interest, there are also practical needs associated particularly with energy and environment. And one of the important examples, for instance, it's a transportation security of liquefied natural gas. Because, in liquefied natural gas, the gases are compressed in a certain form, like, in containers. And when they start to transport in the ship, they might actually separate because the gas is not a unique gas, it's actually a mixture of gases. And we might have a situation when a heavy gas will appear on the top of the light gas, causing the instability to occur and actually damaging the entire process of shipment. Another example is that for instance, we might need extensive interfacial mixing in the process of industrial processes such as water purification. However, what we see here, so it's a picture of the acid mine drainage from the California, when the California Gulch mixes with an Arkansas River. And despite, in this particular case, in contrast to this case, we really want this mixing process to occur sooner, but the interface between two very well miscible fluids, it remains stable at a global scale. Essentially, we need to take a big spoon and to mix it, or to force it with acceleration to mix it in order to destabilize this interface. So premixed and non-premixed combustion is just another example. And I would like just to emphasize that when we talk about premixed combustion, it's usually in combustion community called fires, whereas non-premixed combustion, whereas premixed combustion in the combustion community is called flames. So it's an example actually of two different sort of processes. Now, I would like to now pronounce some very sound words, but I do mean it, because interface actually is a source of paradigm shifts in science, mathematics, and engineering. And in fact, the problems of the interface dynamics, it's actually one of the cornerstone problems of modern, I would say, science and mathematics, including nonlinear sciences, because this problem is related to the third prospect, so-called third prospect of Landau, who was a 1962 Nobel laureate. And resolution of the first two prospects, the first and second of Landau, were also rewarded with Nobel Prizes in 2003. One of them was the superconductors, where it was shown that another types, there is a second type of superconductors. And the second one, it was actually in the first one, actually, it was the first phase transitions, where it was shown that the Landau theory of phase transitions has some, let me put it in a nice word, overlooks or considerations. So it's actually a problem associated with the magic and mystery of science and mathematics. This is a very ancient picture. It's a Moscow 1965. I don't know whether it's good to show this picture these days, but in any case, it's history, right? So it's a United States USSR workshop. And people who are sitting here, it's Andreev and also Pines. And people who are standing here, it's Khalatnikov, who was the founder of the Landau Institute for Theoretical Physics, Rusinov. Then Pitaevsky, it's a Gross-Pitaevsky equation. Then this is Abrikosov, Nobel Prize laureate, Kadanov, and Bardeen. So what we have here, these people here, Abrikosov and Kadanov, these were people who were associated with the resolution of the first and second prospect of Landau, even though Leo Kadanov unfortunately did not get the Nobel Prize, even though he was supposed to for the phase transitions. Whereas Bardeen, I think he was his mentor during his postdoctoral studies, and he's a twice Nobel laureate, the only probably physicist who got the Nobel Prize twice. And I'm placing the picture of Lighthill here, because even though there was not probably direct connection between Landau School or Lighthill School, but Lighthill School of Applied Mathematics, it does process through the more formal approaches for solving, formal mathematical approaches for solving problems, whereas Landau School, it actually was focused more on a physics, side of analysis. So in this case, we tried to implement actually the best sides of the features that we have. And I'm now coming to the governing equations. So the governing equations may look like killing, but again, like, whenever you are taking a look at them, please, as I mentioned, breathe in, breathe out, and trust. Essentially, I will walk you through. So what we have our governing equations, and the first, because it's a sort of a tutorial discussion, I would like to mention the first difference. With these governing equations and also the boundary conditions and also the entire problem, the way we solve it in an inertial frame of reference. This is not a frame of reference that moves with an interface. We don't presume the constancy of the interface velocity. We stay in an inertial reference frame. And the velocity of this inertial reference frame is V naught, which is here. We have the conservation of mass, momentum, and energy, as well as the heat flux equation, actually here, right? And we have also the equation of state, which we may presume that it would be a equation for an ideal gas. Our x-axis and t is actually a three-dimensional problem. It's a three-dimensional spatial coordinates and time. These are the fields of the density, velocity, pressure, energy density, and heat flux, which might be defined in one fluid or in the other fluid. Our energy density depends on the internal energy, also on the velocity of the fluid motion, and W is an enthalpy. We have a multi-phase dynamics, that is, all these fields and quantities are defined in the heavy fluid and in the light fluid. We have a free boundary, that is the interface, which is described by some scalar function, which is 0 at the interface and is positive or negative. It's a sort of a marker function inside one fluid or another fluid. We have the normal and tangential vectors of this interface, and we may define the boundary conditions at this free boundary, which is actually might be defined this particular way, even though this is actually sort of a local definition, because we may not presume that the interface actually might be always a well-defined function. It may require more accurate consideration. So if this would be, it's not all, because in addition to that, we need also to prescribe the boundary conditions at the outside boundaries of the domain. We also need to prescribe boundary conditions for the thermal heat flux, and we need to prescribe the initial conditions, which are initial perturbation of the interface and the flow fields, which actually impose additional symmetries in the flow, additional boundary value problems, and characteristic time scales and length scales. So if this would be only these three equations, like, the conservation of mass, momentum, and energy, and the density would be constant, and we will add here, for instance, the viscous term, it would be Navier-Stokes problem, for which we all expect to have, like, maybe some resolution to be obtained solved, and, like, $1 million prize issued. But here we have a more complicated situation, because in addition to the equation in the bulk, we have also the boundary conditions at the unstable interface, at the outside boundaries of the domain, conditions for the thermal heat flux, which was not known up to the point when I will discuss, and as well as the initial perturbation. So in this sense, it allows me to state that actually this problem is even more challenging than the Millennium Navier-Stokes problem. Let me consider, like, what sort of boundary value problem we might have at the unstable, freely evolving, essentially nonlinear interface. There are two types of free boundaries, and I would be calling them interfaces and fronts, even though sometimes, the definitions can be confused, but in general, there are two types of them. So this quantity, which is presented here, G tilde, is a mass flux across the moving interface. And in case when we have just mass flux, like, there are no sources at the interface, we have that actually all these quantities which are placed in a square brackets, and this is actually, these square brackets are defining the jump of a function at the interface on the both sides of the interface. So we have that the mass is being conserved, which is this first equation. Then the normal component of momentum is being conserved. Then the normal tangential component of momentum being conserved, and also the energy flux is being conserved. And these equations are known as Rankine-Guggenot conditions. The difference between what is done before and actually what we are doing here is that we do this all in an inertial frame of reference. So we are not doing it in a frame of reference associated with the motion of the frontal, etc. So as a result, it's actually pretty general equations that can be applied at any moment of time. One more thing is that even though we consider here only, like, thermally conducting fluids or ideal fluids, it can be essentially magnetohydrodynamics, it can be anything else, because the technique that we are using, it allows us to indeed to identify pretty broadly the situation. There might be also a specific situation when not only the jump of this function is equal to 0, but the function itself, which is sitting inside the parentheses, equals to 0. So it actually, as we define it from here to here. In this case, we have a front that might have 0 fluxes across it. And we have different set of the boundary conditions because all these conditions are reduced to these conditions where you have continuity of normal component of velocity and pressure at the interface, and discontinuity of tangential component of velocity and enthalpy at the interface. About the heat flux condition, it's a very tricky condition for both numerical models and also for analytical situations. In our case, I think we were able to formulate it accurately. And in case when we have fluxes across the interface, so we're talking about the fluxes, we presume that actually wherever the interface actually is a sort of a level line or a level surface for internal energy. So actually the heat flux should be always normal to the product of the heat flux and tangential of the interface should be 0. Whereas, for instance, in Rayleigh-Taylor problems, like, where we have fronts with, for instance, under the effect of radiation, right, we should have a different situation, and actually the heat flux should be tangential to the interface. And boundary conditions are, of course, different. So wherever I'm discussing here, we are looking on the left side, we are not looking on the right side. So whatever will be on the right side, it will be actually the talk on Thursday. So now, in this case, when I'm talking about the boundary value problem, I'm not telling that this fluid is like, fluid 1 and the other fluid is fluid 2. We actually define the fluid boundary similarly to what we have been doing with the actually the derivation of the equations and the boundary conditions in an inertial frame of reference. We define them pretty broadly. So we're not saying that this is a particular fluid or that is a particular fluid and the fluid is miscible, etc. No. We say that this is actually the fluid phases are broadly defined. This can be different kinds of matter. This can be the same matter with distinct thermodynamic properties. The matter may experience phase transition. It can also may have change in chemical compositions, be out of thermodynamic equilibrium. It might have non-diffusive interfacial transport. And I think, as I mentioned, in under conditions of high energy density, as I mentioned before, we might have interfaces with significant fluxes, macroscopically observable fluxes at the very, very tiny thin interfaces. So boundary value problems should be solved. All this, as I mentioned before, at a nonlinear freely evolving interface, we don't know what they are. And I just would like to mention that boundary value problems are in generally very challenging to solve, which actually explains why people not solving them a lot. Because, whenever we solve a differential equation, or if you go to a standard course in a differential equation, the professor tells you, there are two types of boundary of problems that we need to solve to identify what the integration constants are. One of them an initial value problem or a Cauchy problem. And these problems, they usually can be solved, and at least for some finite time. And the other type, it's actually boundary value problems. And boundary value problems, in contrast to initial value problems, even if the equations are perfect and boundary conditions are perfect, everything is perfect, boundary value problems may or may not be solved. And if the solution exists, it may not be unique. It may be actually shown in a number of examples, which I will not be focusing here. However, solving boundary value problems has important advantages because in this case we treat the problem rigorously. We actually, all we do when we solve boundary value problem, we count balances on the right and on the left. On the right and on the left. We ensure that there are no losses somewhere in between which we are not accounting for. We may approach actually the problem by using a number of powerful theoretical methods that have been developed in the past, and we may identify the physics of the process. What is good in terms of application is that we may identify reliable benchmarks for diagnostics, and these theoretical approaches are usually free from adjustable parameters because we do count all the fluxes on all the sides. And the theoretical results, as a result, might have a high predictive probability in a broad parameter regime. In general, historically, whenever we have a big success on the time of science, we talk about solution of a boundary value problem. So I will be skipping probably the dynamics of fronts here. Maybe maybe focusing more on dynamics of interfaces. And I just would like to mention that stability of interface separating distinct, we may call it miscible if you would like, but they're not necessarily, we just have a certain mass flux across the interface. Fluids is a long-standing problem. Classical approach to the problem was developed by Landau in 1994. He actually found, he solved the problem in a certain approximation that is described here. Essentially, he studied, I don't know, maybe I will be, it sort of freezes here. Yeah. So he studied dynamics of a phase boundary with application for flames and premixed combustion. consider it ideal in compressible fluids, balances the fluxes of mass and momentum, implemented a special condition for the perturbed mass flux at the interface. He did not consider energy equation, and postulated constancy of the interface velocity. And Landau found that this interface, under these conditions, is unconditionally unstable, and this instability is called Landau-Darrier instability. It's also known as a Darrier-Landau instability, depending on the community to which you talk to. There were important challenges with both Landau-Darrier and Darrier-Landau instability, and these challenges were the following. So this result, in a sense, contradicted experiment, and actually not just one experiment, but a number of experiments. Because stable flames, they exist and they're observed in the laboratory. And the achieved consensus since 1994, community were trying to resolve this paradox, was that interface is stable at small scales due to some microscopic effects. It's unstable at global scales, which are actually challenging to set in the laboratory and to rigorously study in the laboratory. And interface is globally unstable, even if we have a zero acceleration. And this is the formulation of the third prospect of Landau, as I mentioned before, 1962 Nobel Prize laureate, which we're actually trying to address. It's maybe some incomplete list of seminal studies of the interface stability, and you can imagine how many careers have been developed, how many successful approaches have been developed. Furthermore, when people were trying to resolve the problem, they actually built the foundations of the nonlinear physics and applied mathematics, because this sort of equation, what is this? It's actually complex systems. It's a generic mathematical model when we have actually complex beta and d coefficients, which actually complex Ginzburg-Landau equation, which may be reduced to nonlinear Schrödinger equation in exactly integral system, or Kuramoto-Sivashinsky equation, amplitude equation, reaction diffusion equation, etc. We may work with this sort of equations also in statistical and quantum systems, in statistical physics and quantum system, and proceed with this theory of phase transitions in solid, liquid, gases, and glasses, or as condensed matter physics such as superconductivity, superfluidity, Bose-Einstein condensation, Gross-Pitayevsky equation. And similarly, these sort of systems start to have an even broader impact when we discuss stochasticity and chaos as a scale-dependent and scale-invariant complexity in very complex phenomena. So a lot of very powerful, very mighty community, huge amount of careers, but we still would like to understand the nature. So we are not arguing with this. We actually say that yes, absolutely, in a certain approximation, the problem can be solved one way or another. We would like to approach it from a different perspective. So we develop a general framework for a broad range of conditions. We find the mechanisms of the interface stabilization and destabilization, and we found the new class, the entire class of fluid instabilities that were not previously discussed in ideal and realistic fluids. One thing that I will be telling you, I will tell you the principles, key ingredients, and outcomes, and then I will come to the formulas, because formulas, they may be even more killing than the words. And I don't encourage you to read all these words, actually, that I place it here. I place it, actually, the words purposefully on the slides, because I do speak with a certain accent. And sometimes for people, it's easier to see rather than to hear and then translate it one more time. So the theory should be physically meaningful and mathematically rigorous, because we need to analyze the dynamics in a broad range of conditions, including ideal and realistic fluids. We need to relate to Landau's framework, show actually what were the missing points. And we need to link also, be able with a group theory approach for nonlinear and similar dynamics of the interfaces, essentially connecting interfaces and fronts such as Rayleigh-Taylor instabilities. We also need to solve the boundary value problem, presuming that flow fields may experience very sharp changes. The dynamics is usually observed from a far field. So, even if the interface is diffuse, we look at it like that, not like that. So essentially, even if it's a thick, if you look at it from a far field, it appears to us quite thin. And we actually also presume that very tiny, small-scale processes might be very challenging to diagnose, because we are talking about something observable. The key ingredients of this analysis would be, the first thing is that our interface velocity, whatever it is, we don't presume that we know what it is. And it's free from the postulate of the constancy. We represent the flow fields very formally, and we derive them in each of the particular circumstances. We accurately account for the thermal effects and rigorously define the flow field structures. And then we identify fundamental solutions. And when I'm talking about fundamental solutions, if we are talking about a linear sort of problem, we're talking not only about eigenvalues, where all the researchers usually stop, but we also include the eigenvectors. And when we have eigenvectors, we actually know what is the structure of the solution, how the flow fields looks like. And I already mentioned the main yields of this analysis is that the interface is stabilized by the macroscopic inertial mechanism, balancing destabilizing acceleration. Microscopic thermodynamics and thermal heat flux produce vertical structures in the bulk, whereas macroscopic fields in the bulk are linked to microscopic transport at the interface. And Landau solution, as I mentioned before, is just a perfect mathematical match. So now it's a picture scheme. So what we have two fluids. They have certain rho v at the infinity on the one side, rho v at the infinity on the other side. There might be also acceleration, which may be destabilized, directed from the heavy fluid to the light fluid. We might have the fluid being thermally conducted. So essentially, it might be applicable for both ideal and non-ideal fluids. So actually, this is the chi thermal conductivity, E, rho, and pressure, which is actually related to the light fluid. The same quantities are related to the heavy fluid. We slightly perturb the flow field here. And we actually have an interface being initially flat, which is actually marked with the dotted points. And then we may perturb it. This perturbation, of course, is presented here really exaggerated because the small perturbation should be small. It's 2 to 1% of the amplitude wavelengths. Now, this is a methodology. And this is the point where we do need to breathe in and then breathe out. Because what we do now, in order for us to calculate the conditions accurately, we apply generalized distribution functions in an inertial frame of reference. We presume that our interface velocity v tilde might be set equal to the steady planar interface velocity, but in general case is not equal to it, because we know how it is associated with the mass flux across the interface. Then we expand the flow fields. We expand them formally, keeping in mind that any vector field may be represented as a gradient of a potential function plus curl of a vector function. And this is what we do and what usually people do not do. However, what this representation allows us to do, we really can see how the vertical fields are being created, what is the source of the vertical field, and when this vertical field, what is the structure. Then we also define the thermal heat flux, and the thermal heat flux here is defined actually rigorously here from the Rankine-Gougueneau conditions when the jump of the thermal heat flux is coming here. And what I would like to mention is that traditionally the heat flux is actually calibrated by the enthalpy of formation, which is included here in W node. However, we see that this creature is more delicate because if, for instance, we look in an incompressible limit, we need to account for also the characteristic temperature and the kinetic energy, which is actually G large. It's actually rho v, our large, zero order mass flux. As a sample case, we consider two-dimensional dynamics, but it can be done in three-dimensional case as well. So we have characteristic length scale lambda of initial perturbation, characteristic wave vector, and we use characteristic time scale. Now, we have the flow fields in the bulk. In each of the bulk, it doesn't matter what it is. That includes the potential of the fluid, the pressure perturbation, the vertical field, then the density perturbation, as well as the internal energy. And we presume that these perturbations, they actually behave on coordinates and time in this particular way. If we have ideal fluids, we have a 3x3 matrix to solve. If we have a realistic fluids, we have a 5x5 matrix because there are 5 vortices, five creatures here. And then in order for us to define the flow field, we make this matrix the equation equal to 0, and then we find the flow field structure. After this is done, we take a breath in and breathe out and substitute all these huge expressions into the boundary value problem, because this is only step 1 and this is a step 2. And when we substitute them into the boundary value problem, we might be able to identify what is actually our characteristic potential for the one fluid, the other fluid, what is the interface perturbation, what is the vertical field, and what are the internal energies, which is actually, as you may see here, EH and EL. So in general, if I will be talking about ideal fluids, we are talking about a system of equations that has 4 variables. That is potential 1, potential 2, vertical field, light fluid, and also interface perturbation. If we are talking about, so it's actually a 4x4 system. If we are talking about realistic fluids, we have a 6x6 system. So we should have potential 1, potential 2, vertical field, interface perturbation, and we have 2 internal energies on the one side and on the other side. So it's a pretty complicated structure. So now, in order to show how things work, because it will appear surprisingly, because the primary mechanism is a macroscopic inertial mechanism rather than microscopic thermodynamics we actually better start from ideal fluids, and in this way we also resolve the paradox of Landau. So what we have? Conservative dynamics. We have our leading order expansion, leading order terms. We have actually incompressible limit. We have our z-order conditions, and we have also the first order conditions which are derived here. So we have the conservation of mass, conservation of normal component of momentum, conservation of tangential component of momentum, and conservation of energy, which is written here. Our interface velocity is also perturbed, and we know what the perturbations are. After we find the flow fields in the bulk, this is actually our structure, we see that the potential and pressure are associated with one another. The light fluid and heavy fluid, whereas the vertical field always stands aside. And it's an important, not only observation, but it's actually an important physics fact that the vertical field is not dynamic in nature. Vertical field is energetic in nature. You may see it actually from the structure of the equations. So from this, we build our characteristic vector, four-dimensional. We substitute it, and we try to find the solution. And we start with an inertial dynamics, and I will show you the conservative dynamics and Landau dynamics, so we will see, like, how the things work. Again, I repeat my boundary conditions. I substitute all that into these equations, like, solve the matrix M, which is presented here, and we find the solution. A good thing, good note is that we have four variables: potential 1, potential 2, vertical field, and interface perturbation. Actually, I list them in the other way, so it would be potential 1, potential 2, interface perturbation, and vertical field for convenience. We have exactly four fundamental solutions. Two of them are stable. It's omega 1, omega 2. The complex, the imaginary part is presented here. It goes, like, with the square root of density ratio, and R here is a density ratio. And there are two other solutions. One of them is very unstable, and the other one is stable. So according to our, without, like, considering the structure of the flow fields, we would probably say that, oh, this probably, we would not even know whether this conservative dynamic is stable or unstable, because always there is an unstable mode. However, the good thing, like, about the sense, let us actually consider this solution one by one, and looking at the structure of the eigenvectors, we may derive the flow fields. So in this case, we will call the solution our CD as a conservative dynamics, which is actually a combination of these two solutions. So for our dynamics, because we have four solutions, four fundamental solutions, four independent variables, we have a non-degenerate dynamics, and this is actually can be seen from the structure of this matrix here. This is how the solution looks like. So this is a perturbed flow fields, it's perturbed streamlines, and this is the pressure. The interface is somewhere here, and these pictures were presented were plotted at the time where we did not learn how to put, like, theta function in the plot and make it the uniform. We have this capability now. So, but I mean, in any case, so this is what we have in the light fluid and in the heavy fluid, and it's clearly seen here that the flow field is potential. So the stable dynamics with the stable oscillations is potential in the bulk, no vorticity at all. What is interesting here is to look actually at the pressure perturbation. Here the red is marking the high pressure region, and blue marking is the low pressure region. So what we see is that the interface is indeed oscillating like this, and the pressure is directed from the high to the low like that, and we see these perturbations like this. So we do remember that we had essentially two other solutions. One of them was very stable, and the other was very unstable. However, for one of them, we may put the integration constant arbitrary because it has zero flow fields. And the fourth one, we actually should make the integration constant equal to zero because it does not satisfy the boundary conditions. So at the interface, this is, for instance, the solution 3. And we see that for all of them, for all the perturbations, including pressure perturbations or the velocity perturbation, we will have actually a situation when we have a zero perturbed flow field. So whatever the integration constant is, it doesn't matter. And this solution is not actually occasional. It appears all time when we derive it. Would it be ideal fluids or non-ideal fluids? And it's associated actually with the fact that our choice of inertial frame of reference is arbitrary. So it's actually not a random creature that sits over there. And the solution number 4, which actually appears as a stable solution, we actually should make it by hands equal to 0 because it has doesn't satisfy the boundary conditions at the infinity, and it has, for instance, the vertical field, which increases at the infinity far away from the interface. So this is actually the choice. Now let us look at Landau solution. within exactly the same framework. So we have a conservation of mass, conservation of momentum, conservation of normal component of momentum, conservation of tangential component of momentum. We do not have conservation of energy as we had in the conservative dynamics. We have a special condition postulated by Landau for the continuity of normal component of velocity at the interface, or which is actually equivalent of the postulate of the constancy of the interface velocity. In a very similar manner, we will find the solutions, and we will surprisingly find, if you will open textbook, for instance, Landau-Lifshitz, there are only 2 solutions there. However, there are 3 of them. So there is actually one unstable, one stable, and one omega-3 is the same as it was before, with this, with zero flow of fields. So our integration constants, actually our solution, which we really need to look at for the instability of Landau-Darrier, it's a solution number 1. For the solution 2, which is a unstable, which is a stable solution, we need to actually put integration constant equal to 0. Whereas for the solution 3, it can be arbitrary integration constant because for similar reason it has 0 perturbed flow fields. What is interesting here, that again, as before, we have exactly the same 4 variables, right? Which is actually stated here. So we have potential 1, potential 2, interface perturbation and vortical field, 4 variables. We have 4 equations. However, our system has only 3 fundamental solutions. On the mathematical side, the degeneracy of this behavior is clearly seen from here, because if we will be representing this actually matrix in a proper form, like a standard form, we will see that for the matrix PL, which is actually multiplied by R dot on this side, one of the rows is just equals to 0. So it's actually the degenerate matrix. On the side of physics, it actually has a deeper meaning, because Landau solution, specifically this condition, it leads to the energy imbalance at the interface. In fact, this condition, it makes the entire system, or the entire Landau solution, incompatible with the energy conservation at the interface. We either may prescribe conserve momentum, or we may conserve energy, but we cannot conserve both of them. And as a result, we have our omega-1 solution, which is actually Landau-Darrier instability. So omega-3 and omega-2, I think we handled them before. So this is my omega-1 solution, Landau-Darrier instability. We see that the structure of flow fields is quite different. You see immediately the appearance of vortical field in the bulk, which is here seen among the streamlines. And you see that the structure of the pressure field, it appears quite different. Rather than oscillating this way, from the heavy to light, it starts oscillating like, side by side, essentially creating this vortical field as you may see it from here. Furthermore, we may evaluate essentially what is the characteristic problems of the vertical of this vertical field, and we know what would be probably the smallest characteristic length scale, because this vertical field is in general has a very large length scale. So our stable solution, even though it might have similar structures, it should be actually made integration constant equal to 0, because again we cannot satisfy the boundary conditions in the infinity. So this is how things are done. So what we have an interesting thing. When we conserve, we have in both cases exactly the same structure of solutions. So potential 1, potential 2, interface perturbation, and vertical field, right? In both cases, we have four conditions, 4 boundary conditions: conservation of mass, conservation of momentum, normal component, conservation of momentum, tangential component. In conservative dynamics, energy is conserved. In Landau dynamics, there is a special condition on the normal component, which is actually incompatible with energy conservation. So the question is, what is going on? Why in one case we have unstable dynamics, like Landau-Darrier instability, whereas in the other case we have a stable dynamics, and these are well-defined perturbation structures. So in our case, in order for us to better understand it, let us consider the interface velocity in a laboratory frame of reference. We see actually that in our case, this interface velocity, it may not be constant, and it will experience the slight perturbations, which we may see from this side. So for our conservative dynamics, and it would be true for both Landau-Darrier instability or for our situation for conservative dynamics, because all our equations are derived in an inertial frame of reference. So for the conservative dynamics, this term, u dot and naught, experience slight oscillations. Another term also experience slight oscillations, and as a result, the departures of the velocity from the steady value, they also start to experience steady oscillations. So what we see, we are coming to the inertial mechanisms of stabilization. So what has happened, and let me actually maybe illustrate it with a figure here. When we had a planar interface, we had some balances. Now, when we perturb the interface, so what happens? Light fluid follows the perturbation, heavy fluid follows the perturbation. So the fluid follows the perturbation, and it would be actually correct, would it be compressible, incompressible, viscous, unviscous, because this is just the physics meaning of it. So what we have a situation when we start, because the fluid flow follows the perturbation, we start to change the momentum. We started from inertial dynamics, no external forces, no any losses. Inertial dynamics, ideal fluids, we did it purposefully. So if we have an inertial dynamics, momentum should be conserved. As soon as we start to perturb the system, we start to change the momentum. And in order for us to conserve the momentum, the only way for us to do it is to actually slightly perturb our position of the initial interface, what it was. So essentially what we are getting, that in our conservative dynamics, we will have perturbations being stably oscillating, and also the interface velocity as a whole also will be oscillating together with them. This mechanism is actually absent in Landau-Darré instability or Landau solution, because what happens here, we have a postulate. It's so inobedient, this red spot. We have a postulate of the constancy of the interface velocity. And as a result, if the interface perturbations start to grow, we cannot change the interface velocity because of the mathematical postulate. And as a result, the Landau-Darré instability develops. So what we have from this picture is essentially that Landau-Darré solution becomes for Landau-Darré instability becomes a perfect mathematical match. So what we see here is that indeed, when interface is slightly perturbed, I repeat, parcels of the heavy and light fluid, they start to follow the perturbation. This causes a change of momentum. The system is inertial, so momentum should be conserved. And in order to conserve the momentum, interface as a whole should slightly change its velocity. As a result, we have a reactive force or a propulsion force occurs and stabilizes the dynamics. In the classical Landau instability, this mechanism is absent because of the constancy of the interface velocity. However, what we see here also why the instability occurs, why this term actually can be actually balanced. Because if we will be looking at the interface velocity from the perspective of Landau solution, what we have that both of these two terms, they grow exponentially with time. However, because of this condition, of the constancy of the normal component of the velocity at the interface, they are artificially made equal, their sum is artificially made equal to 0. So in a sense, in this case, it tells that actually that the classical Landau dynamics is a perfect mathematical match. It's not like a solution that might be physically conserved, but it's a perfect mathematical match. Now, there are certainly differences between conservative dynamics and Landau dynamics. Like, in one case, we conserve mass, momentum, and energy. In the other case, we don't conserve energy. In one case, we will have slight oscillations of the velocity near the steady value. In the other case, we have a postulate. In one case, we have a potential flow of fields. We have potential flow of fields. It would be for the conservative dynamics. In the other case, we have a vertical field that is being present. We have a shear free dynamics in both cases, and we have different mathematical properties, such as non-degenerate dynamics in one case and degenerate dynamics in the other case. We have stable dynamics in one case and unstable dynamics in the other case. And now this is why I'm emphasizing the need in solving boundary value problems, because just change of the one condition of 4 makes these big dramatic differences, observable differences. However, how these things would be seen? Yeah. If this would be, for instance, our conservative dynamics, we will have the flow of fields, like, in a laboratory frame of reference being like that. So it's actually a streamline where we already account for the background motion velocity. And in this case, we have Landau-Darré instability. In other words, we might not be even, we need to super precise measurements to be able to differentiate between these two. Now let us look at the accelerated dynamics. We repeat exactly the same sense. And we will have actually the situation when we will have the acceleration g being present here, divided, making the dynamics stable or unstable depending on the strength of this acceleration. So if the strength of the acceleration is greater than critical, we will have an unstable dynamics. When the strength of the acceleration is smaller than critical, we will have a stable dynamics. However, in both stable and unstable dynamics, what we will have a potential flow field in the bulk here, and potential flow field in the bulk here. So as soon as we conserve mass, momentum, and energy, at the interface, flow field is potential. That's actually a kind of statement. What is interesting here is that the structure of the pressure becomes somewhat different. You see there is actually a sign here that actually pressure, even though they look similar, I mean, they're actually somewhat different because the color code in the upper figure is somewhat different in the numbers in the lower figure. However, in a sense, like, the high pressure region is located here, the smaller pressure region is located here, so we actually have a pressure pushing from the heavy to light, forming a spike. And similarly here, we will have a pressure from the light to heavy, directed from the high pressure to lower pressure, forming a bubble, as it's presented here. So the mechanism of stabilization and destabilization in this case appears that if I will be writing that in a dimensional form, that there is a critical value of the acceleration that depends on the density ratio. It also depends on the velocity of the of some velocity scale. And if we will be sitting below this region, then we will have stable oscillations. If we will be sitting above this region, we will have unstable growth. And we may also evaluate actually that the stability of this accelerated conservative dynamics is set by the interplays of the inertial and buoyant effect or by the reactive force and gravity. We may evaluate what would be the maximum growth rate of this instability and what would be the critical growth rate of this instability, critical wavelengths, and we may evaluate this ratio. This ratio is actually quite important, especially in the problems associated with like ablative Rayleigh-Taylor, because it may tell actually us what should be actually the resolution of our simulations or the resolution of our observations in the experiments. Certainly in Landau situation, in Landau solutions, such things don't happen. And again, since we still have our 4 equations, 4 variables, like, because of this force condition, which is actually postulate of the constancy of the interface velocity, we have a different solutions for the, our omega-1 is a proper solution, whereas the 2 others should be motivated differently, and this is actually the characteristic flow fields. So with and in this case, in Landau solution, we do have a vertical field in the bulk, in contrast to conservative dynamics, which is potential in the bulk, potential everywhere. Potential in the bulk, it also potential, it does not have any share at the interface. So I will be skipping the Rayleigh-Taylor dynamics because we sort of know what it is, but in fact, actually, we have a similar set of equations. We have stable and unstable mode here, and we have, again, situation for the flow fields. I would like to point your attention, even though quite often we keep in mind that our flow fields can be arbitrarily, one can show precisely actually in Rayleigh-Taylor instabilities that the flow field should be potential in the bulk, and we might expect intense velocity shear at the interface as it's presented here, similarly to conservative dynamics. Now, if I will be presenting all these things here, and we are talking about ideal fluids, what is the purple? It's our instability of the conservative dynamics, right? So it's stable below the critical value, and it becomes unstable above some critical value. Dark blue, it's a Landau-Darry instability, and light blue, it's a Rayleigh-Taylor instability. And what we see, when we sit above some specific value of acceleration, where all these collide with one another, coincide with one another, we see that our conservative dynamics instability becomes actually the envelope for everything. It has the largest growth for a given density ratio at for large acceleration values. So again, the properties are very different. I will be probably just emphasizing them, that we, in conservative dynamics, we conserve mass, momentum, and energy. We have interface velocity in the unstable regime being a time-dependent value, and in the stable regime. We have flow fields which are potential in the bulk. We have also the shear-free velocity field. We have non-degenerate dynamics, and stability is set by the interplays of the inertia, which is reactive force, and the buoyancy, which is actually gravity or acceleration. Landau-Darry instability is different, as we discussed it before. It has a vertical field. It does not conserve energy, and it has a degenerate dynamics. Whereas in Rayleigh-Taylor, we have a situation when we conserve mass, momentum, and energy. We have zero, actually constant interface velocity. We also have potential flow fields in the bulk. However, in contrast to what we have for a conservative dynamics, we have an interfacial shear. And in this case, we also have a degenerate dynamics because for 3 variables, we have only 2 solutions. And actually, our third solution is an analog of Richtmeier-Merkov instability because it actually it depends on the interfacial shear. So we sort of understood that whenever we conserve mass, momentum, and energy, and when we have an interface that is being perturbed, which has mass flux only, ideal fluids, no microscopic effects, nothing else, just because of the fact that we should have inertial dynamics in the absence of acceleration, we need to have additional macroscopic stabilization mechanism, which we call inertial stabilization mechanism. At present, would it be ideal fluid? Would it be realistic fluid? And this mechanism, actually, because it's macroscopic, not microscopic, it actually becomes the primary mechanism of the stabilization. Now we would like to consider the realistic fluids, and I would like to repeat the same sort of exercises, right? Presuming that we have a subsonic conservative dynamics, for instance, in realistic fluids, we again make our leading order expansions. So we have actually thermal conductivity, which is described by the characteristic Q, which is heat flux. We have our conditions for the heat flux, meaning that the heat flux is actually normal to the interface. The tangential component of this heat flux is actually equals to 0. And we have these Killian equations for the first order, which would be actually the conservation of mass coming here, the conservation of momentum coming here, the perturbation of the heat flux condition, that actually all these come here. The good thing about this sense is that it's all doable if you will be a little bit more patient. And there are some new things that we would like to point out that actually people, I think, might be overlooked in the earlier studies. But I'm not putting saying that, oh, something was overlooked. The surprising thing is not that something was overlooked, but the surprising thing that this still can be solved. So in this sense, I would like to proceed probably to solution here. So what we have now in the bulk, we have, again, for every fluid, would be one or another. We have potential, pressure, vertical field, density perturbation, and internal energy perturbation. We would like to see what the structure of the flow fields is. And if we prescribe some initial perturbation with a wave vector k small, we want to know what is our wave vector k large is. There is a sign minus here, but it also can be plus, depending whether we look in the upper domain or a smaller or in the lower domain. So in order for us to do so, we need to substitute all these flow fields perturbations into the governing equations and have our 5 by 5 now, not 3 by 3, but 5 by 5 matrix. And the surprising thing, when we start to calculate the determinant of this matrix to see what our structure of the wave vector k is, we see that the vertical field, which is actually omega divided by v, stands separately from all other coupled quantities. So vertical field does not want to have any relation with the potential or with the pressure perturbation or with the perturbation of density. It just stands separately by the structure of this equation. As a result, we have actually a fourth order equation with some known coefficients, which depends on the parameters of the system, and they can be solved, in fact, in any limit. And if I would like to solve them for arbitrary, for instance, Mach number or for arbitrary thermal conductivity, Mathematica is able to solve it. It just declined to print it because the equations become too cumbersome. But in principle, this can be calculated for essentially any value of the parameter. What is important here is that when we may define actually two important scales, and the relations between the scales will be actually telling us in which regime we are located. The first of the scales is actually the ratio between rho v and chi, which is the thermal conductivity, or in simple words, particularly for people who work with ablative Rayleigh-Taylor or ablative Lichtmeyer-Meshkova instability, because this is what it is. It's a m dot divided by chi. So it's actually a characteristic mass flux, rho v, divided by thermal conductivity. This quantity sets the characteristic wavelength, in our case wave vector. So it would be actually m dot divided by chi. And the ratio of this km, large km, to the wave vector of initial perturbation is a dimensionless parameter. So you have a characteristic length scale set by m dot and chi and thermal conductivity. And we have a characteristic length scale set by initial perturbation. Their ratio might be large or small. So this is actually one thing. And the other thing is the ratio between rho v squared and characteristic pressure, or I would say the modified Mach number. It's not exactly the Mach number, but it's a modified Mach number because we actually don't care what is the characteristic gamma here. Depending on what is the ratio between these parameters, actually km to k, which is dimensionless parameter, which may be very large or very small. and also the ratio between this parameter and also the characteristic Mach number. So because even though they, we might have a situation when Km to K may be very large, where is a Mach number very small. We might have a situation when the Km to K may be very small, but the Mach number is still small, but the dynamic will be dependent on who is going to zero sooner. So essentially, we need to solve, in a sense, L'Hopital. We used to need to use L'Hopital rule anytime and very accurately. That's why we needed all these actually mechanisms to solve this problem very rigorously at each and every stage to calculate where we are. And depending what is the ratio between these parameters, we may sit in the advection regime, diffusion regime, or a low Mach regime. I call this regime low Mach just like, deliberately, essentially. Maybe there might be a better title for it. But advection and diffusion is actually sort of standardly defined. What is important? That even though we have these complicated structures, we have our 5-variable flow field, right? These 3 regimes have in common 4 mechanical waves, which are exactly the same waves as they were for the conservative dynamics in ideal fluids. So essentially, only some 2 energetic waves, which are associated with the energy perturbations, they're coming in each particular way, they start to behave differently. However, all these 3 waves, 4 waves, which is actually the potential of the one fluid, potential of the other fluid, vertical field, and also the interface perturbation, they are the same in each of the regimes. So system continues to know what it was, in its ideal mechanical world without caring about microscopic processes. Same thing actually happen if I would like to introduce, like, for instance, surface tension effect, or maybe some viscous effect. It doesn't matter. System still will keep in mind where it was initially, what was the ideal state. Now, we have now 2 other waves, which are energetic waves, and they are regime specific. And more important, that they are not only regime specific, but they also defined by the seeds of the energy perturbations. In fact, they defined by what is seeded by the thermal heat flux. So it actually imposes on us the requirement to define the thermal heat flux very, very accurately. So we cannot just scale it with the enthalpy of formation. It's a way more delicate feature, and I will be discussing this a little bit later. So, however, if these seeds are absent, even the fluids are non-ideal. So actually, if we manage to precisely balance energy flux at the interface, like, make it, for instance, zero on both sides, in this case, even in realistic fluids, thermally conducting fluids, we will have a potential motion on both sides, and this would be stable oscillations in a small gravity, a small acceleration regime, and some unstable growth when we have actually very large acceleration values. And again, in each regime, the interface velocity is known a constant value. Would it be one regime or another regime or a third regime? So let me actually just, go one by one. So in the advection regime, so what we have that our characteristic length scale, characteristic wave vector set by the m dot and thermal conductivity, so it's actually rho v divided by chi, is much greater than the characteristic wave vector set by the initial perturbation. So it goes to infinity. And there is also another value that goes to the infinity, so our pressure is very high. So it's actually just the inverse of the Mach number. In this case, our energetic modes, our 2 energetic modes, they have a particular dependence in the heavy fluid and in the light fluid. And this is how our growth rate looks like when our Mach number approaches 0. It may be actually written for any Mach number, just as soon as we would like it. So we know that the interface may be stable or unstable for some acceleration value, which we defined, with as a threshold defined by the G critical with a tilde. And we know, that in some limits, we may reduce it, for instance, to this particular form. Now let us look at an interesting picture. So what is this? And you see that we significantly progressed because now we not only just present, one subdomain on another, but we can merge the subdomains and put an interface in between. So what is this? It's a velocity flow field. And this velocity flow field, it contains potential and vertical component. And it contains vertical component solely because we have perturbations of the energy and we have seeded perturbations due to the imbalance of the thermal heat flux. If this thermal heat flux, Q, whatever value is absent, we have potential motion in the bulk similar to conservative dynamics. Otherwise, we have the small scale vertical structure. So this is the perturbation of velocity. This is perturbed streamline. This is our vertical field. And the strength of this vertical field, I repeat again, depends on the thermal heat flux. This is our pressure. And you clearly see, like, that how we have a pressure pushing from the heavy fluid to the lighter fluid, forming a bubble, and pressure from the lighter fluid pushing to the heavy fluid, forming a spike, the other way around, I'm sorry. So this would be the spike and this would be the bubble. This is our energy perturbation, and we see that our energy perturbation, internal energy perturbation, are quite anisotropic in one fluid and also in the other fluid. And furthermore, in the light fluid, we have our energy perturbation being very well correlated with the vertical structure, with a characteristic vertical field. So this is one regime. What about the other regime? We have another sort of consideration. We have our Km divided by K being smaller, much smaller than 1. So in a sense, m dot divided by chi is much smaller than characteristic wavelength, so diffusion effect. And we have our Mach number not being small, but it actually being smaller than this parameter Km. So it actually goes zero even quicker. So in this case, we have a diffusion regime. And our energetic modes, they have a different structure, because in this case, we actually, our energy perturbation impose additional motions, which actually lead to some additional motions of the pressure field through the density perturbation. So it's not like, a direct sense, but it may be represented this way. We may evaluate the growth rate. It would be different. It would be similar in some regards. And in some regards, it would be different. And in this case, we find that our interface may be stable or unstable if we have a different value, like, G critical with a hat, which is different from the G critical with the tilde in the advection regime. And what is, again, like, if we will be considering, for instance, the limit when this value just approaches 0, right, we may calculate what will be the values of this characteristic growth rate. And this is how the flow fields looks like. Again, what we have is a perturbed flow fields, is a streamlines, is a vertical field. This is a pressure, same picture. We have formation of bubble when there is a pressure from the heavy fluid, right? Formation of spike to the light fluid, and formation of bubble when there is a pressure from the light fluid to the heavy fluid, like, forming a structure. We have completely different picture for the energy perturbations, because when we had an advection, it was a strong anisotropy. Essentially, for the advection, if I will go here, right, for the advection, the energy perturbations, they were attached to the interface on the side of the one fluid, and they were, like, going far away, very strong from the side of the other fluid. Here we have a symmetric distribution, essentially, and we have that, like, there is a small perturbations on both sides. And again, there is some correlation between these energy perturbations and the vertical field, which is being formed in the bulk. And now, the low Mach limit. I call it low Mach limit because in this case, essentially, our Mach number is approaches 0, but it doesn't approach 0 as quickly as our characteristic Km value. So in this sense, actually, our Mach number become a bigger, smaller parameter compared to the thermal to the parameter set by the thermal conductivity. Our energetic mode, actually, they have most cumbersome structure here. They actually start to produce more and more features here. We may still calculate them, and we may identify the initial growth rate, and we may consider, what would be the characteristic values. And I kindly point you parameters. There are these values like epsilon here, right? Epsilon 0h, epsilon 0 light here, right? Similar picture was here, right? When we have epsilon 0h, epsilon 0 light here. And similarly, it was here. It was sitting everywhere in the increment epsilon light, right? 0 light, which is here. Where are they coming from? These are the seeds of the energy perturbation. These are the seeds of the energy perturbation as soon as we actually scale them with an internal energy and also with a mass flux, because it's an energy flux. So depending on what are they, we may have vertical structure. If they are 0, there is no vorticity. So, and here I would like to show one interesting feature, because what was before, it was a unstable regime. Now I'm showing the flow fields in the stable regime. So what we have here, we have the velocity flow field, which is here, with a vertical structure sitting here. We see these vertical structures in the light fluid very well being formed, right? We see that these actually structures appearing here and here. What is the point? We have vorticity, like, uniformly seeding the entire bulk and our interface is stable, is not unstable. And the picture, if you will be comparing, for instance, with the unstable interface, is quite different. There we have, when we have an unstable interface, verticity actually achieves the maximum at the interface, and it decays vertical field away, far away from the interface. Whereas in the stable regime, we have a different situation. We have that our vertical field is just uniformly distributed through the bulk. And in this case, again, same picture. We have a situation when our flow fields start to be stably oscillate because it's a stable regime. We have a still internal energy perturbation, and all this vertical field is essentially started to be created by the thermal heat flux which occurs at the interface. And actually, when we comparing these results to our previous results, we sort of, I would like to put forward a somewhat provocative hypothesis, because traditionally what people think about how turbulence should be created is that, like, we have a sort of a laminar flow that should move very, very quickly. And in this laminar flow, we should start to develop instabilities. And as soon as the instabilities occur, they immediately will lead to turbulence. In fact, actually, what we see from here is that as soon as the dynamics is interfacial, it remains interfacial. As soon as the interfaces grows, whether it would be interface with mass flux or with zero mass flux, like in Rayleigh-Taylor, it's essentially interfacial. So the maxima of all the quantities, they occur in the vicinity of the interface and decay far away from the interface. So in a sense, according to our theoretical results, in order for us to have a stability, to have actual vertical structure seeded everywhere through the bulk, what we need to have a stable interface, and we need to enable energy flux across this interface and some noisiness at the boundary conditions far away from the interface, because otherwise we would need to make the structures equal to zero. But if we will have some noisiness, like some slight perturbations over there, we have a right to keep them. So this is the entire zoo, if I would like to tell, but I would like to point your attention at this purple line, right? The purple curve. So it's first stable. So it's actually it's an imaginary component, complex component, and then becomes unstable. And this, our instability of the conservative dynamics, that is defined by the balance between reactive force and gravity, or between the inertial effect and buoyancy, which is actually stabilized by inertial stabilization mechanism and destabilized by the acceleration. This instability for ideal fluids has the largest growth rate compared to all others in realistic fluids, and it's a sort of an envelope of all other instabilities in the strong acceleration regime. I think the red one, I think it's describing the advection dynamics, and I would say, like, this one, yellow one, right? It describes the diffusion or a low Mach number dynamics, because they might behave similarly in a certain parameter regime depending on what the thermal heat flux is. But we may always select it like that. So the blue two curves, like, here and here, the light blue is a Rayleigh-Taylor instability, and the dark blue is Landau-Darrier instability in the gravity field. So the letter G that stands here, it actually stands for the gravity. So what we see is that for strong accelerations, that our growth rate for conservative dynamics for ideal fluids that is being strongly accelerated, it envelopes all other growth rates, which is actually quite important, because in this case we can always tell what would be the worst case scenario. We know what it is, right? We don't need actually to care about, like, tiny details. And we know what it is because the primary mechanism for interface stabilization is a macroscopic inertial mechanism. It doesn't care about microscopic details. And it's a somewhat, like, orthogonal to what people actually have been thinking for a very, very long time. But this is actually the result of the rigorous analysis. And I would like, yes, yeah. Thank you so much. I'm about to actually point attention about the thermal heat flux. So again, here we have the situation when we have a balance between inertia, reactive force, and gravity, or inertial stabilization mechanism and destabilizing acceleration. The question now about the microscopic thermodynamics. So what it does, like dissipation, thermal conductivity, even surface tension, because it's still a microscopic effect, it does provide with additional stabilization. But it's not the main reason for interface to be stabilized. It provides with additional stabilization, but it doesn't provide it's not the actual reason for interface to be stable. Thermal heat flux, however, and actually these microscopic thermodynamics, they do impose important qualitative change. In a sense, they set the vertical field in the bulk. In other words, if we manage to handle the thermal heat flux very accurately at the interface, with a reasonable accuracy, not super high accuracy, but with a reasonable accuracy, we may have a potential flow everywhere, in the bulk and in the interface, which essentially means that we can control the dynamics very tightly. So essentially, this is thermal heat flux is seeded by the internal energy perturbation. And in fact, it tells us how accurately should we define it. So traditionally, we may think about that as an enthalpy of formation, which is in my case is defined as a W naught with a bar here. But it's a more delicate creature. Essentially, what we need to do, we need to take our entire energy, deduct from it enthalpy of formation, deduct from it, like, CP times temperature, deduct from it our kinetic energy as a whole, and only then evaluate the characteristic energy perturbations. And from that, actually, it doesn't matter for us, would it be a thin interface or a thick interface, because our calculations are all conducted in the inertial frame of reference. And in fact, our series defines the interface as a place where balances are achieved. So I'm ready to come to the conclusion. Thank you so much for your patience. It's a very nice, very patient and attentive audience. It's a great pleasure for me to discuss these results here. And I would like to mention that our outcomes is that we resolve challenges that we have not been addressed before, specifically defining the structure of flow fields, connecting them to the thermal speed flux, and finding the dependence of the system fields coupling on the system parameters. And this is actually quite important thing, because what we see that, quite often for us it's challenging to quantify the interfacial transport. Quite often we even do not know what the interfacial transport is and where is the interface is, because if the interface, if you look at it from far field, we cannot measure it, diagnose it like, at a very small aperture. But what we may do, we may measure the flow fields in the bulk far away from the interface. And this we can do very accurately. And if we manage to do it very accurately and cautiously, we may tell actually what happens at the interface, because the bulk adjusts, not the other way around. The bulk adjusts. We found the new class, the entire class actually of the fluid instabilities in ideal realistic fluids. We show that the primary mechanism of the interface is, as I mentioned, repeating maybe one more time, but repetition is a mother of knowledge. So in any case, so the primary mechanism of interface stabilization is an inertial mechanism. And in fact, this resolves the third prospect of Landau, because we find that our Landau solution is in fact a perfect mathematical match. And we might have a lot of other applications in a broad range of processes, including supernova, fusion, etc. So interface is a place where balances are achieved. Interfaces are real, even they may not be visible. Interface is not a well-resolved tiny line. We may not care what it is, but what we do need to care is to count balances on one side and on the other side and ensure that there are no losses. And in this case, actually, interfaces in general are globally stable. Would it be, ideal or realistic fluids? And they can be forced to destabilize by some acceleration. In perspectives, I'm happy to discuss it if there is some time. Yeah. If there are any questions.
Thank you very much.
Thank you so much.
So if there are any questions, you can enter them in the chat field. And you have questions here. I guess I'll start off the questions. I'm curious how your analysis changes and what kind of solutions there would be if you included interface diffusion. And
it wouldn't change much. I mean, I do have mass flux across the interface because rho v is rho v, but we may introduce additional fluxes. We may introduce whatever fields you would like, because the way we define the boundary conditions, it would be actually through the use of generalized functions. So we actually calculate the boundary conditions from the governing equations, and it may be added, but it will not change the situation.
So it doesn't change the growth rates at all, or?
It will influence the growth rate. For instance, like, as I mentioned, here, this growth rate, like, for instance, like, marked in red and yellow, right? They're different from the purple one. But in a sense, like, so it actually, because it will be providing some additional stabilization. It will be stabilizing in addition to what it's already been stabilized. But it will not be like a sort of a, so essentially, like, comparing it or influencing it, we may actually evaluate, quantify this effect.
Does it affect where you go from having an imaginary component or or not?
It may influence, yeah, because actually you see, like, you know, that in fact, this is actually a very good question. Thank you so much. Because, you know, for instance, if you have a diffusive interface like here, or for instance, advective interface, right, they becoming stable or unstable at different values of the acceleration. Yeah, they will be influenced. In this regime, yeah, we will have, like, you know, the steel mechanism being, like, you know, the sort of a hero, right? But here, it's some way more delicate features, and they require a lot of different considerations. And in fact, what is presented here is just one of the limiting cases, because, as I mentioned earlier, like, you know, you might have two other parameters, right? In a sense, actually, in my case, like, you know, I deliberately take off one of the parameters and kept just the other one. Because, like, you know, I wanted to have something being on the light fluid, not on the heavy fluid, but it may be something else, certainly. It definitely will influence, especially if you will be sitting in this regime, and it will be influenced quite significantly. It will be actually quite interesting to look at. But I mean, whether this analysis allows to consider, absolutely. If you want to have magnetic field, no problem. Whatever, tell me what you want, and I will give it to you after some calculations.
But mainly, I'm curious about like the multi-scale problem in which you have some microphysics happening on the very small scale, and we're doing hydro at a higher scale, and having some analytic technique that allows us to connect the two would be rather neat, I think.
Yeah, exactly. This can be done. And one of the things that we may actually do here, because, you know, as I mentioned, we do need to look at the structure of the fields in the bulk, rather than, like, you know, because from the structure of the fields in the bulk, we may actually tell what happened, what should happen at the interface. Specifically, you know, if you have some vertical fields in the bulk, for me, it would be already an indicator that there is some energy imbalance at the interface. And this is actually exactly why Landau solution has a vertical field, whereas conservative dynamic doesn't have any vertical field. So, but in Landau solution is actually being imposed, like, you know, essentially by hands. So it's like, you know, ad hoc thing, even though very nicely done, like, you know, to confuse, I mean, to be a point of discussion for 80 years. I wish I would make such point of discussion myself ever, but still, like, you know, whenever we have some vertical field, it's associated with some energy imbalance at the interface, physically. So in a sense, yes, we may measure it. Yes, we may tell what it is. And yes, it can be the point of the link between, say, MD simulations and CFD simulations, if there would be a need, for instance, in such studies. There is actually one more thing, maybe especially of interest to fusion problem, because one of the things that we have found here is that, like, you know, that the interface velocity is never constant. When we have a stable regime, it stably oscillates. But when we have an unstable regime associated with the growth of the perturbation, the interface velocity also increases. So we not only have a growing perturbation, but we have the growing perturbations that move as a whole with a velocity whose magnitude increases with time. So in a sense, we might expect that all these things, like, you know, coming to the hot spot, they might be coming sooner than we expect, just because the entire sense move. So it's not like, you know, that we start to grow, like, you know, like this, right? We start to grow and move together like in a train. So which may be actually additional thing. We discussed it, like, you know, in the paper, but in brief, but I'm happy to elaborate if needed.
Okay. Thank you. So there's also a question online from Steve Hahn. Is there an experiment that might show changes predicted by this analysis compared to traditional Rayleigh-Taylor instabilities?
Is there an existing experiment?
You didn't specify, but I suppose, yes.
I would say that the existing experiments, they already sort of confirmed that analysis, because, like, in Landau, the instability, even though it has been predicted, it has been a challenge to observe in a laboratory in a proper form factor. I know that there were some experiments done in France, for instance, where people actually sort of made using Markstein, like, you know, parameter and many other parameters, so trying to select some parameter regime to show that this might be the Landau instability to occur. However, one should be, I would say, I would be more cautious, more accurate making this statement, because essentially, if you talk about Landau instability, the parameter regime in which it's supposed to be observed, it's very challenging to achieve in experiments. But whether we may potentially make a model experiment, fluid dynamic experiment, I would say that yes, we may, because in this case, what we need to control acceleration very tightly. We need to control initial conditions very tightly. In principle, with the modern day technologies, this is possible to do because, you know, everyone has a computer, a laptop on a desktop, on a desk, right? So essentially in this computer, we have a terabyte of data, like, you know, sitting, like, you know, some in a finite size hard drive. So it means that each and every data point is defined there with a super precise accuracy, meaning that there are the mechanisms and there are the, I would say, manufacturing possibilities to tightly control whatever we want to control. Whether these are being implemented in fluid dynamic experiments, as far as my knowledge, to experiments that already have been presented, I would believe that these experiments require more improvement. In terms of the analysis of the plasma experiments or like fusion experiments, my more recent experience actually it shows whatever the data are, if we have raw data, we will be able to get information from there. If there are data, you know, because making a control experiment is one thing, but analyzing existing data and showing, like, you know, whether there are the tails of this phenomenon that we described is a separate thing. So essentially, by using even the experiment is imperfect, such that it cannot be a design control experiment, which is very challenging to make, we still, by applying advanced methods of data analysis and by working with raw data, we still might get information and actually tell which experimental parameter may require some improvements.
Okay. Thank you. Are there any other questions? If not, let's thank our speaker again.
Yes, thank you so much. It's actually the longest talk I gave on the subject. So maybe I owe a coffee of all of you. So thank you so much for your kind attention and for your valuable time. And I'm very glad that I had the opportunity to present this work and to discuss it with the lead experts. Thank you.
Thank you. And Snejana will be giving another talk on Thursday at 11 o'clock.
Yeah, it would be a different one. So it will not be about the mathematics. It will be way more physical.
Bye-bye, everybody.
Thank you.